Hi, this is Math 1120 remote delivery for May 5th, 2020. This is part 1 of 2. We'll talk about counting and Bayes' theorem. Use this to control the throttle on the presentation. Just a word of encouragement, winners never quit and quitters never win. That's what Vince Lombardi said. So don't stop believing. If at all possible, do not quit. We can do this. And please realize that the final exam is a mandatory requirement. You will be okay. We're going to review counting techniques here using the multiplication rule. We'll talk about things called permutations. We'll talk about things called combinations. And we'll solve counting problems involving permutations with non-distinct items and compute probabilities involving both permutations and combinations. Now suppose you went to a restaurant and the restaurant would let you get 2 choices for an appetizer, 4 choices for an entree, and 2 choices for dessert. Well, you see, you would take 2 times 4 times 2 again to get this many total choices. So that really leads us to the multiplication principle, which says if a task consists of a sequence of choices in which there are P selections for the first choice, Q selections for the second choice, R selections for the third choice, and so on, then the task of making these selections can be done and you multiply those numbers together. Those are independent selections. So, for example, the International Air Transport Association assigns 3 level codes to airports. For example, Fort Lauderdale is FLL. So how many different airport codes are possible? Well, there are 26 letters here, 26 letters here, and 26 letters here. You can reuse them. It's 26 cubed, or 17,576 airport codes are possible. Now that's if repetition is allowed. Here you have 3 people from a 14-member committee are to be randomly selected to serve as chair, vice chair, and secretary. The first person selected as chair, the second is a vice chair, and the third is a secretary. How many different committee structures are possible? You see, the people cannot be more than one of these office. So how many ways can you pick? The first one is 14. Once you've done that, there's 13 ways you can pick the next one, and there's 12 ways you can pick the third. So that is a little bit over 2,000 different committee structures are possible. Problem 31 is a good problem if you want to test your understanding. We often use the factorial symbol, which looks like an exclamation point, but in factorial is you take n times n minus 1 times n minus 2 all the way down to 1. You multiply all those numbers together. 0 factorial is taken to be 1, and of course 1 factorial equals 1. This is convenient to use these conventions in writing some of the formulas. So suppose you've just been hired as a book representative for Pearson Education. On your first day you must travel to 7 schools to introduce yourself. How many different routes are possible? Well, you have 7 schools, so 7 ways you can pick the first one, then times 6 for the second, times 5, times 4, times 3, all the way down. That's 7 factorial. This is how many different routes are possible because you're picking them in sequence without repetition. Problem number 33 is a good one to perfect your understanding with. Now, sometimes order matters. So a permutation is an ordered arrangement in which R objects are chosen from n distinct different objects. And R has to be, of course, less than n, and repetition is not allowed. Now we use a symbol n permutations taken R at a time to represent the number of permutations taken. So you see P and R is going to be this number, but if we multiply top and bottom by this, we get this complicated looking formula. But that is the formula, and there are ways for you to do this with a calculator, and you should know how to do the NPR with your calculator. You can look that up under the permutations, but that will simplify this calculation. So the objects have to be distinct, repetition is allowed, and order is important. Then this is the formula. Look at an example. In how many ways can horses in a 10-horse race finish first, second, and third? Well, there are 10 horses. It matters who finished first, second, and third, so order does matter. They're distinct horses, so it is 10 permutations taken 3 at a time. It is this divided by this. 10 minus 3 is 7. So it's 10 factorial over 7 factorial, and you do these multiplies and you get that. Or you could say there's 10 ways you can finish first, 9 ways you can finish second, and 8 ways you can finish third. And if you multiply all that together, you get 720, and you can get this from your calculator as well. 45 is a good example to test your understanding of this. Now sometimes order doesn't matter, and a combination is a collection without regard to order in which R objects are chosen from indistinct, and once again R is less than or equal to N, without repetition. And the symbol is in combinations take an R at a time, or sometimes I say in choose R. And so this is the number of combinations of in distinct objects taken, R at a time. So here's a problem. Roger, Ken, Tom, and Jay are going to play golf, and they randomly select teams of 2 players each. What are all the possibilities? Well, it doesn't matter if you have Ken and Roger or Roger and Ken as long as they're on the same team. So this is all the listings. So here's Roger and Ken, and here is and Ken and Roger is not a different one, so this is how many ways. So you see order does not matter here, and this is 4 combinations taken 2 at a time. So we end up there are 6 ways, 1, 2, 3, 4, 5, 6 ways to choose 2 from 4 players. And we can find a formula by knowing the only difference between that is you're dividing by, it's going to be a smaller number, so you divide the permutations by R factorial, and this is a formula that we will see on the next page. Okay, so to summarize, the number of combinations of indistinct objects take an R at a time. The objects have to be distinct, repetition is not allowed, and order doesn't matter, is given by this formula. Again, your calculator has buttons like this that you can type in to make the calculation easier. So here's the question. How many different simple random samples of size 4 can be obtained from this? This would be like if I have a class of 20 students, how many different ways could I pick 4 students to go to the chalkboard altogether? Well, you see the order, they are distinct, there are 20 full students, and the order in which they're selected is not important. Either they go to the board or they don't. So it's 20, choose 4. We do the calculation, and we get there are almost 5,000 ways to do that, to pick 4 from 20, or 20, choose 4. 51 is a good problem if you want to test your understanding of that. Now here, a DNA sequence consists of a series of letters representing the strands that spell out the genetic code. And you have these different acids, so you have A, C, G, and D. Okay, so the question is, how many distinguishable sequences can be formed using 2 A's, 2 C's, 3 G's, and 1 T? Now it's important that you realize that you can't tell the difference between these 2 A's. So you're talking about saying, oh, I have 2, 2, 3, and 1, so that is going to be 8 slots that I'm picking things. So the task 1, this is going back to the fundamental, this is the restaurant problem. So you choose where am I going to put the A's, and then I'm going to choose where I put the C's. Then I'm going to choose where I put the G's, and then I'm going to choose where I put the T. Well, you see there are 8 choose 2 ways that you can pick the A. There are 6 choose 2 ways that you can pick the C. There are 4 choose 3 ways that you can pick the G, and there are 1 choose 1 way that you can pick the T. You're stuck with that. So you see you're multiplying all these things together, so you have quite a complicated formula, but you get there are 1,680 possible sequences that can form. So in general, what you do is the number of permutations of n objects, of which n1 are of one kind, n2 are of a second kind, and ... nk are of a kth kind, is this ratio. It's n factorial over n1 factorial times n2 factorial times nk factorial, and n is the sum of all of those. So you do have to add in the things that happen even one time. Here's the problem dealing with that then. How many different vertical arrangements are there of 10 flags, but 5 of them that are white, you can't tell the difference, 3 are blue, you can't tell the difference, and 2 are red? Well, the formula using what we have is 10 factorial over 5 factorial representing the white, 3 factorial representing the blue, and 2 factorial representing the red. We don't have to write 1 factorial because that is 1. And problem 55 is an opportunity to perfect your understanding. Now here is a problem. In the Illinois lottery, an urn contains balls numbered 1 through 52, and 6 balls are randomly chosen without replacement. And so a player chooses 2 sets of numbers to win. All 6 numbers must match what is chosen from the urn. Again, the order doesn't matter. What's the probability of winning? Well, there are 2 chances to win, but how many different ways can you pick 6 numbers from 52? That's 52 choose 6, and that's over 20 million, so it's going to be 2 chances of winning out of 20 million. Let's talk about acceptance sampling. A shipment of 120 fasteners contains 4 defective fasteners was sent to a manufacturing plant. They randomly select and inspect 5 fasteners. What's the probability that exactly 1 of the fasteners is defective? Well, the solution is there are 4 that are defective, so first you pick the defective. How many different ways you could pick the defective is 4, choose 1. But then the rest of them are not defective, and so you're picking 1 here, but the others have to be picked from those that are good. So you see there were 120 altogether, so we're picking the remaining 4 from 116. So you have to do both these calculations. That's going to be 4 times this 7 million number, and you get 28,640. And so you see the probability of getting 1 defective fastener is going to be 4, choose 1, times 16, choose 4, divided by 120, choose 5. We do all of those calculations and we get about 15%. Problem 61 is a good one to test your understanding of that concept. The last topic for the day is medical results. And so assume cancer has a 1% prevalence rate, meaning 1% of the population has cancer. And then the probability of having cancer is P of cancer is 0.01. And so what we're going to do is we want to talk about what is the probability you have cancer given that you get a positive test result. Now, the false positive result rate is 10%, and the true positive rate is 80%. And so the solution is we have to go through and calculate that. So assume we have 1,000 subjects with a 1% percentage rate, 10 have cancer. And so that means the sum of the entries in the row of the first values is 10. But the other 999 do not have cancer, so that is going to be 999. So of these, 10% get positive results, so 10% of the cancer-free subjects in the second row get positive test results, so that gives you 99 in the second row, and so on. So what we really are doing is looking at a table that looks like this. And so you see, if you get a positive result, what you're going to have, it is going to be 0.01 rather, times 0.8 divided by the sum of those two probabilities, and is only 7%. And this is called Bayes' formula. Now, more than ever, time is precious. Each day must count. Do the math, it'll make you strong. And now, more than ever, take care of yourself and of